is Elena. I'm a PhD student at the University of Manchester, and first of all I'd like to thank the organizers for allowing me to talk at this conference. And today I'm going to tell about my work. So in my talk I will start from the motivation. I'll provide some motivation for the problems considered. I will begin from the part of my work that has already been completed about scattering on the collinear defect in the discrete lattice, and then move towards the work ongoing about waveguides with the transversal defects and how waves propagating them. So I will discuss the appropriate transforms we are going to take in this for this geometry, validate on the example of the half plane on how describe the method, and I will derive the matrix Wiener-Hopf equation for my waveguide, and finally I will end my talk with some conclusion remarks. So a few words about motivation. It is well known that there are several so-called canonical diffraction problems, such as scattering of a plane wave on a semi-infinite half plane, on a finite strip, or scattering of a waveguide mode on a on some defect or screen in a waveguide. But in my work, I'm interested into the discrete counterpart of this continuous problem, and in my case, my problems are formulated on the discrete square lattice. So why we're interested in these discrete problems is, firstly, since on our square lattice we're going to solve the discrete Helmholtz equation, where the Laplace operator is in fact just a finite difference approximation of the continuous Laplace operator. So therefore our discretized Helmholtz equation we're going to solve for the square lattice is just an discretized analog of the one for continuous acoustic problems. So yeah. And another thing is that our square lattice, we can imagine it as the system of small masses which are connected together with the elastic links, and equation of motion for the antiplane displacement for the lattice nodes for the time harmonic case for such a system can be produces the discrete Helmholtz equation, the same one as I was talking before. So this model is used widely to model wave propagation in different contexts, such, for example, in solid mechanics, and some phenomena in solid mechanics, to model wave propagation in some materials with periodic structures like acoustic metamaterials, for example, and many others. So yeah, that was the motivation, and I will start from formulation of the first problem, where I'm going to consider scattering of a plane wave on the collinear defects on the square lattice. So we're going to solve the discrete Helmholtz equation, where here the Laplacian is a discrete Laplacian, formulated for the total field, which is the sum of the incident field, incident wave, which is a plane wave, and the scattered field we are going to find. We can formulate the dispersion relation for the lattice, and we are going to employ the limiting absorption principle as the radiation condition to make sure that our scattered field is decaying at infinity. Oh yeah, important to say, so in this case the defects in the square lattice are the cracks. So how I model them is that I assume that the links between the red dots here are broken. So they are not interacting with each other. This is our boundary condition. So for simplest case where we have a semi-infinite defect, we can obtain an exact solution via Wiener-Hopf method. So the main difference of a discrete Wiener-Hopf method from the continuous one, is that we're using the discrete Fourier transform or Z transform or Floquet block transform. It's called differently. I'll call it discrete Fourier transform. And U plus U minus here are analytic outside and inside of the unit circle of the complex plane Z. Yeah, so we have two half transforms here. Define this, and we're going to apply our Z transform to the Helmholtz equation, taking into account the boundary conditions. We can obtain a Wiener-Hopf equation. Then we need to factorize the kernel and some split the forcing term, which can be done easily in this case. Here note that the subscript denotes the multiplicative factorization and the superscript, and subscript denotes the sum split. Yeah, and after it's done, we can simply apply the Liouville's theorem for the plus and minus halves of the equation and find the solution. So the main difficulty in my case with the finite defects, with numerous finite defects, is that instead of just one edge of the crack, we have several edges. So we need to split our discrete Fourier transform not in two, but in twice as many unknowns as we have in our, as how many defects, edges of defects we have in our system. So therefore our scalar Wiener-Hopf equation turns into the matrix Wiener-Hopf equation. And our kernel for this problem is now a matrix. So we know, and will probably be said many times later, that factorizing a matrix is not an easy task, and an approximate method has been suggested recently for factorizing, which allows to approximately solve the matrix Wiener-Hopf equation. In particular, it allows to avoid direct factorization of the matrix kernel and replace it with the sum split. So in iterative manner, we can obtain a solution with quite high accuracy. So this method has been originally developed for the continuous setting for the class of equations as follows. And yeah, the main difference with ours is that here the matrix entrances, some of them have these exponents that are obviously grown in exponentially at infinity. So, and in our case, we have at most algebraic growth here at each entrance. So this is technically, it should be easier to factorize. Well, however, we're going to use this approximate method for some reason. So the method can be summarized as follows. We can basically rewrite our matrix equation as the coupled system of scalar equations, where on the left-hand side we have two unknowns, and on the right-hand side we have a forcing term which consists of some known function and of all the other unknowns in the system. And on the first iterative step of our method is we are going to completely neglect the contribution of this unknown part here on the right, solve the first scalar equation, take our solution and substitute it to the second equation in the system, to the right part. Then solve the second equation for the next pair of the unknowns, take the first two solutions, well, it would be U1 and U2, substitute it to the third one, to the third equation, and so on, before we reach the end of our system. And then, once we have solutions for all the unknowns, we take them and substitute them back into the first equation, therefore performing a full coupling of the system and starting the second iteration. So on the simplest example of a single finite crack, our solutions for the unknowns can be rewritten as follows, where one depends on another, as you can see here. And on the first iterative step, we are going to take this red term over here as 0. Therefore, we have a solution for U2, substituted to the second one, and so on and so on. So we can run our iterations as many times as we want, but in fact, we just want our solution to converge up to the accuracy of the rational approximation, which is required for the functions k and j here, in order to do the sum split on each step. And the method indeed converges within just a modest amount of iterations, so from just 3 or 4 to 5 or 6 for more complicated geometries. And the main benefit of this method is it converges faster for the bigger defects. So here are the examples of the scattered field, and this work has been published. If you're interested, you may have a look. And now I'm going to move towards the work which is ongoing, which is a scattering of waveguide mode in a discrete waveguide on the transversal defect. So now we have our discrete Helmholtz equation, and the boundary conditions on the waveguide walls and the screen are Dirichlet. Again, we're going to find the scattered field. The incident wave now is the waveguide mode. We have dispersion relation. We are using the limiting absorption principle. So this problem is also motivated by its continuous analog. We have a continuous waveguide with a finite strip embedded in it, and a Wiener-Hopf equation has been obtained for such geometry in this paper of Paris and David. The main feature of the waveguide problem is that, as you remember, for the collinear defects in the lattice, we transformed our Helmholtz equation. We take the transform along the defects, and in this case, due to the finiteness of the vertical axis of the waveguide, we can only take the transform in this direction. So in this paper, they use the sine and cosine transforms, where the integrands automatically satisfy the boundary conditions on the strip, the sine, and the gaps on the cosine. But we have a discrete setting, so we need to introduce some analogues of the sine and cosine transforms, which will be defined as follows. So I call them odd and even discrete transforms, which are basically just an analog of the sine and cosine, but in a discrete setting, and the inverse transforms for them are defined as follows. Okay, so now I will describe the method on the example on the half plane. So now we have the Helmholtz equation and the Dirichlet boundary condition for the field on m equals 0, n is negative. And our incident field is the plane wave. So we can show for such formulation that the field is symmetric with respect to m equals 0. And employing this fact, we can obtain the additional boundary condition for our positive n. So now we have a system of boundary conditions. For negative n, we have Dirichlet. For positive n, we have something like this, which is in fact just a discrete analog of the Neumann boundary condition. So now what we're going to do is to apply the odd discrete transform to our scattered field for negative ends, and the even discrete transform for the positive ends to our Helmholtz equation, and therefore we can obtain two difference equations for some new functions phi and psi, where phi and psi are the combinations of the half Fourier transforms. Now the next step, we can obtain the ansatz for these two equations. We can write it down in such a form where B and C are the unknown coefficients, which we will express like this. Now we're going to pick two equations from system 3 here for n equal 1 and n equal 0. So it's the row on the edge of the strip and the adjacent row. And from these two equations, keeping in mind the definition for phi and psi, if we add them together, we can obtain a scalar Wiener-Hopf equation for some new functions L minus L plus. Now we have a kernel here and F forcing term. The kernel is just a square root. We know how to factorize it. The forcing term only has simple poles, so we can also sum split it by the use of the pole removal technique pretty straightforwardly, and therefore obtain the solution for the phi of n equal 1 and psi of n equal 0. So the solution for the half plane is expressed like this. Yeah, it would be nice to compare this result with the known result from Sharma, which was obtained by the classic approach of taking the Fourier transform along the defect. But this is a work ongoing, so I'll do it later, hopefully. And yeah, now coming back to our waveguide problem. So now we have the duct walls with the Dirichlet boundary conditions on them, and instead of positive ends and negative ends with different boundary conditions, we will have three regions now: the gap below, the gap above the strip, and the region perpendicular to the strip. So yeah, as before, we can take the odd transform to our sigma b perpendicular to the strip, and the even transform to the regions in the gaps. Obtain now two difference equations. One is one has this term r on the right, and one hasn't. So now, since we have three regions, we have three ansatz for this problem: phi 1, phi 2, and psi. Using the boundary where phi 1 and phi 2 are defined for the lower and upper regions here. So using the boundary conditions, we can eliminate the unknowns B1 and A2 from the first two expressions. And now, similarly to the case of the semi-infinite strip, we're going to pick now two equations from the system at each edge. So one for n equal 2, one for n equal 2 plus 1, and same for the lower half, which will allow us to eliminate all the unknown coefficients here in the ansatz. And the resulting equation is a matrix Wiener-Hopf equation, where this matrix M is a square 4x4 matrix, which has the form which is similar to the one in continuous case, as we expected. So our functions s and c here are the analogues of the sines and cosines. And as we know from the continuous formulation, in case of the symmetric waveguide, the problem can be reduced to from 4x4 to 2x2. And we can show that it indeed happens for the discrete formulation as well. So for symmetric waveguide and the odd incident mode, the amount of unknowns from 4 reduces to 2, basically. So the resulting equation is like this. So this matrix, this is the kernel, and yeah, in the continuous case, it has been shown that this matrix 2x2 can be factorized directly. We would expect that it is possible as well in the discrete case. Yeah, so it is important to say that we can also directly find the exact solution for our problem by the use of the boundary algebraic equation method that allows us to obtain the solution in terms of the Green's function. So in this case, since we are in the waveguide, we will have to use the tailored Green's function, which is defined as follows. So we just add some boundary conditions to the definition of our Green's function. And how we're going to find the expression for it is we're going to take a discrete Fourier transform from this equation, again obtain some difference equation, similarly as before, write down the ansatz for the upper region, lower region, upper region, and the for n equals n naught, where n naught is where our point source is situated. So, and then taking into account 3 now equations for 5 written for n naught plus 1, n naught minus 1. We can find all the unknown coefficients here, and our lattice Green's function is defined as the inverse Fourier transform of the g hat here. Yeah, so this is just an example of some calculations of this Green's function. We can see for different frequencies, we can see the different amount of modes excited. And then if we define a Helmholtz operator, which has, from the property of symmetry, has such a property for any unknown functions, for any functions f and w, and this for our scattered field and our Green's function, we have such expressions for this operator. We can obtain the solution in terms of the boundary algebraic equation method, where here is our scattered field, which only depends on the unknowns adjacent to our strip. It's a finite bound, which can be found by inversion of such a matrix, where each matrix entry is the lattice Green's function. Yeah, so this is just an example of the field. Yeah, and so finally, what is done here, we wrote the solution for the waveguide via the BAE method and derived the matrix Wiener-Hopf equation. The main difference with the continuous case for the matrix Wiener-Hopf equation is that it's written only for the values, for the transforms of the values of the field and not the derivatives, as it is in the for the continuous waveguide. So also for the continuous waveguide with the barrier, the 4x4 matrix is actually not solved. So this they only discussed the 2x2 matrix, and our current form for the discrete waveguide is actually suitable for using some approximate or maybe even exact factorization methods. We're gonna so yeah, this is the most interesting part of this problem for us. And another interesting thing that we are going to check is would be interesting to see if the phenomenon of unusual transmission or reflection that has been shown for the continuous case in this paper, if it preserves when we discretize our waveguide. Yeah, that's it. Thank you very much for your attention.
Thank you very much for being here. We have approximately 5 minutes for questions. Please.
Yeah. Somewhere in slide number 17 or around.
Which one? This? No?
Maybe before next one.
No?
When you none of them recognized. Anyway, so there was a slide where you have shift in n and also was 1 over x. So then you said, well, let's look at n equals 0, n equals 1, and have a scalar Riemann-Hilbert problem, solve it, happy, and so on. But what's the point to solve it for n equals 0 or 1 if all of them are connected? You have infinite system of. You cannot just separate it and solve for n equals 0 because the next one will be have n equals 0 or previous one also.
Yeah, here probably.
Yeah, oh, this one.
Yeah. So we have these answers, and we can express our coefficients b and c in terms of this psi 0, phi 1. So if we find a solution for phi 1 and psi 0, we will find a solution in all the for any phi and psi, basically. So we only need to find these two functions, and if we write down just these two equations and substitute these answers with C and B in a form like this, we can form our Wiener-Hopf equation, which only includes basically four unknowns, since our phi and psi are the combination of u minus 1 and u plus minus 1 and u plus minus 0. And yeah, so the main idea is that if we find psi 0 and phi 1, then we solve the problem. And to find them, we need to solve just this scalar equation for the half plane. For the waveguide, the equation would be matrix, basically. We will have more unknowns, if that makes sense.
Then I don't just involve still follow an equation. If we write the previous equation, it will have an unknown.
Yeah.
And if you said, well, let's look at n equals 2, you will have again a scalar Riemann-Hilbert, and you can solve it. How it will? It basically means that you just have infinite system of equations. And all of them connected. You just look at the couple of them, solve it, but if it's a system, how you will cut just two equations? The next will be connected to the previous one. And,
well, that's the trick. We just express our unknowns B and C here as.
Maybe I didn't understand. Anyways.
Yeah, well, I can explain later.
The idea is that this ansatz goes through, so that's the point.
That's the solution.
Yeah, so it is enough to determine. This is how I understand it. So that this ansatz goes through the equations. So
solution for the entire
well, this is a
system.
statement, of course. This is a kind of probably should be checked.
Please.
Thank you, Elena. It's a very interesting presentation and probably juicy mathematics. My comment is general, but sorry if it's naive, but I wish David were here and I look through those papers of Bazan's papers. The question is, if frequency is very low, your Helmholtz equation becomes Laplace equations. I'm pretty confident all this problem can be treated with conformal math to the problem, and that then you can have something for comparison with your method because you're trying to find something. Is it true? Have you thought about that?
Yeah, well, I'm being asked this question every single time. Thank you. Well, we are not thinking about this problem as the in the limits that leads towards the continuous case, just because mathematically we can't, well, strictly show that it happens. So if we just take the solution and take a limit of the frequency or of the spacing in the lattice, we can show and did that for the solution converged towards, well, limits tend to the solution in the continuous case. Yeah, but
That Davis paper.
Yeah, but yeah, the main idea.
Diffraction duct, so it's 2D full conforming mapping low frequency, no doubt about it.
The question is slightly different. The question is what happens if the limit of k tends to 0,
Correct.
rather than the continuous to discrete. So we're not talking about the limit of discrete to continuous. We're talking about the Helmholtz to Laplace limit.
Well, Bazin has shown that in this case, in fact, the solution for the discrete case, it limits to the continuous solution. It's like just, it can be just shown by hand. Well, in this case, that would be just interesting to see.
Please.
In your first point, when you have several collinear finite cracks, in the continuum problem, no one would try to use Wiener-Hopf, write a system of integral equations and solve them. You say that you can discretize the continuum, and for the Laplacian, that's fine. Try to discretize elasticity. If you discretize elasticity, as soon as you have your lattice with fixed Poisson's ratio, you have to be very careful when you say that any lattice can replicate the continuum. But for the Laplacian, it's fine. If you have square lattice, okay. But then, so if you look at continuum problems, people look at problems like this, they solved it, and derived system for equations, they solved them. By the way, when you consider the lattice, the incident wave in the lattice, you have to treat it as a wave in a dispersive medium. So omega and k should satisfy the dispersion relation. You can't just choose them arbitrarily.
Sure.
So your lattice already has anisotropy, dynamic anisotropy, but suppose that's fine. But if you say, if I look at what people did in the continuum Green's function, of course you have Green's function for the case, and you can derive the system equations that would be, well, similar, say, discrete version of the integral equations that derived in the past. You can say, okay, my knowns are the displacements on the spaces of the crack. Yeah, you have algebraic system to solve it. Happy days. What's the deal? What is the problem here? Why did you choose to go to the Wiener-Hopf?
Well, the main benefit of this method, as I mentioned, is that it might be beneficial for like bigger sizes of these cracks, if we're talking about some like practical problem, there most likely will be many points, lattice nodes with boundary condition on the lattice, and then if, for example, it's a really big system with many defects, as far as I understand, the system of algebraic equations will just become very large and difficult to solve. And for the free lattice, not a waveguide, for example, we also have a double integral.
I agree entirely. As soon as you have a semi-infinite crack, that's fine. There's no question about it. But you said you have a finite number of linear cracks. That's what is in your slide. That's what I'm asking about. If you have finite number.
But what if they are very large?
You didn't say that.
I'm saying it now.
Absolutely.
Yeah.
That's
Sorry.
That's fine. If this is the answer, this is fine.
Yeah, this is the answer. So
Okay.
it might be beneficial for like large length of these cards.
Okay, that's fine.
Well,
Thanks.
thank you very much. I think if there are any more questions left, we can leave them for the discussion session. But right now, I think we have to terminate our pre-lunch session and go for lunch. Thank you very much.